I'll just say that right now, he's a professor of neurology at the University of California, San Francisco, where he spent much of his career. If you can name an award that Stan Prusiner has not won, you'll win a prize. And at the end, I'll actually list some of these formally. But now that you've all settled in, one of the things that Dr. Prusiner wanted to do at the beginning was to reconnect with one of his early mentors at the University of Pennsylvania. So he grew up in Des Moines, Iowa, and then lived in the Midwest, I think in Cincinnati, before coming as an undergraduate to Penn, and got involved in...
What do you think Des Moines is? Do you think that's the far west?
I spent 18,
I'm sorry, I couldn't.
I spent 18 years in Chicago. My daughter did travel soccer. Des Moines was close. Sometimes we would drive to her soccer match, and I thought I would see the Golden Gate Bridge.
I knew it.
So I know the Midwest well. So Sidney Wilson, why don't you come up and join us for a couple of minutes? Sidney is currently an emeritus professor of surgery at the University of Pittsburgh, but these two had a mentor-mentee relationship at Penn, and they wanted to spend a few minutes just talking with one another, with all of you.
Well, it's not like Sidney and I don't know each other, but I thought it would be great to have a little discussion, because it was Sidney who introduced me to research. And this was between the 3rd and 4th years of medical school. And I walked into this lab, and I'll let Sidney take over, because here I was this neophyte who didn't know anything about anything.
Well, one thing I can say about Stanley Prusiner is that he doesn't know nothing about anything for very long. And that was one of the most rewarding parts of my working with him. I was born and raised in Philadelphia. I went to college at the place called the University of Pennsylvania, and I graduated in 1951. So I then poked around a little bit, went back to school, about this time to the University of Chicago. And that was medical school. I came back here to train in surgery, and I was actually a member of the faculty of this institution until 1968 in surgery. But I have to say that if you're born and you're raised and you stay around here, and then you hear about something in Des Moines, that is a little bit like, at the other side of the world. Even Cincinnati is a stretch. So I came to Penn, back to Penn from medical school, and I had something that a resident usually doesn't have. I was very fortunate. I had an R01, an Individual Investigator Award from NIH to do some research. And therefore, I had a little bit of money, a little bit of space. And I thought so much about Stan and his accomplishments that I forgot where he came from, who had sent him to my lab. And I was just talking to him a month or so ago, and he reminded me that it was Dr. Ravden, who to me and to everyone that I knew in the surgical world, in fact, in the HUP, was just the professor at that time. And he was someone that had some connection with Stan's family, I think. Right. But why did he favor me? And I must say it was a favor with Stan. It was because I think I had met him, bumped into him in the Gates Pavilion, which was brand new at that time and had narrow openings. And I was in a cast. I had a full leg cast. So the professor said, "Sidney, what on earth did you do?" And he was very avuncular, almost paternal, like in his concern to me, about me. And I told him that I was skiing in Mont Tremblant. and that I had broken my leg. And then he turned to me with his knuckle, and he rapped it. Dummkopf. So that's what he said. So I reassured him. I tried to reassure him that, well, I was on my research year in the surgical residency, so I wasn't missing any clinical service, and no one was, I could go to the lab and do what I had to do. And maybe that he remembered that when Stan came along, but whatever the reason, I had Stan, and I had gotten involved with hypothermic research, which we used in surgery at that time as simply a means to do research. I mean, there were people doing clinical work, but I had another resident who had a spring-loaded heart valve that he got from the Elgin Watch Company, and we wanted to put it into animals in the lab, but there were only the two of us. Now, that was long before there were any grants. I mean, the department had some money that it could give out to young investigators and so forth, but we had to get the animals in a condition where we could operate on them, and two people had to do the operation. It could not be done really very well by one person. So we figured out we'd use this hypothermia we've been reading about and cool the animals down, stop their heart, operate on it, and then revive them. Well, to just get quickly through that, the result was that during resuscitation from hypothermia and ischemia, there is a problem with brain edema. And resuscitation fails often because there's high intracranial pressure. When the brain expands inside of its box, called the cranium, it builds up pressure and the perfusion blood can't get into the tissue, so there's ischemic damage. And I wanted to find out whether the ischemia that we noted was due to the hypothermia, the swelling was due to the hypothermia or acidosis, which was a byproduct of ischemic metabolism and so forth. And Stanley was there, and we got a project together. Now, with students, I would normally present a couple of possible problems, and if they expressed interest in one, I would assign some reading or recommend some reading, and then we would sit down and plan an experiment. And in the course of all this, of course, a lot of things went across the table. And so Stan got into his work, and at first he was working with another student, and then I could see right away that he didn't really need another student. And so I allowed him to do his thing. Now, he was supposed to meet with me 3 or 4 days later, discuss results. I mean, in the very beginning, we did it together, obviously, but then, and we would discuss the results and then plan another experiment. And it didn't take very long that when I would come to that meeting with Stanley Prusiner, he had done the experiment that we wanted to do. He had interpreted the results. He may have read a little bit about it further, and he had planned and carried out the next experiment, so that we had 2 experiments to discuss.
So let's get
that was very impressive.
Let's get Stan's memory of this. So you,
I have a
Yes,
microphone. Well, I don't remember being
I do.
such a good student. What I remember was that I'm doing this work at whatever pace, and I'm saying, this is really great. I'm doing a puzzle every day. This is really fantastic. And as my life was a kaleidoscope from there on, it started with Sidney, and he taught me so many things, just taught me how to think about data and how to read a scientific paper. You don't just start at the introduction, you read the abstract, you go to the end and look at the end of the introduction, then you look at the highlights, usually the beginning of the discussion, then you look at the data. And then you ask each time, does the data first make any sense, and then is it significant? Is there really a difference, a delta? And you use some simple-minded test, a statistical test. Now, there are many, many more of these, and they're all driven by Excel spreadsheets or something similar.
Not then.
But then you did it. And you had these Marchant calculators, right? Those rolling balls or wheels. And you taught me how to think about the data and to make sure that it was real or whether it was garbage. And the field I've been in for a long time, there's been a lot of garbage along the way.
Well, it's amazing that you say that, because that is my recollection in what I might have tried to get through to you, and that was that you look at the paper, but you look at the data, you look at the numbers and the graphs, you don't look at the conclusions, and even the discussion you sort of wink at a little bit, and you decide what you think of this before you make a decision about your opinion on that paper.
Yeah, and I think that's that's not done quite so often now, because people read the conclusions, and they somehow absorb all these conclusions without really looking at trying to get an answer of yes, it's real, or no, the person's fooling themselves, because there's a lot of times the data's not so good as the authors claim it is. And I don't think it's because the authors are trying to cheat. I think it's because the authors are not very self-critical. And so this approach to science made it clear to me that I really needed to be careful. And as I went along, it saved me a number of times, because I would have gone down the hole into the river below.
So, Sidney, when I first called Stan, he was very keen to have you join us up here. And I think we all owe you a huge debt, because it's clear that you sparked the interest of research in Stan Prusiner. And in many ways, he imprinted on your research style. He's got his own. But we're going to hear in the next little while about, where this story went, how that imprinting and spark of interest in research and creativity and the kaleidoscope evolved. So thanks so much for joining us up on the panel.
One other comment?
Yes.
Over the years, I've followed what Stan has done, and I don't understand it all after a period of time. And I wondered what was in this man that made him persist. I mean, he's had an arduous odyssey. You should read his memoir, Madness and Memory, that came out a few years ago. But I just discovered something. He was rowing. He was in the crew at Pitt when he was in college. And I, for whatever reason, thought he was a coxswain. I think the reason, if you look at him, you would the coxswain on a boat is like a jockey. He's the brains, but the horse has all the brawn. Okay, well, on the boat, the coxswain has the brains, and the guys do the grunt work, right? Well, he told me, no, I was a grunter. I was in the middle of the boat, and I was working it out. So I said to myself, that now makes a lot of sense, because on the boat, the coxswain sits in the back, and he's the only one that sees what's going on. He can see the rest of the field, the other boats. He can judge what should be done. He remembers the plan of how they were going to do it, and he gives orders of cadence, force, and direction. He has a tiller. And so the only rower that sees him is the first one beyond him, which is the last one down, and he's called the stroke. So he starts to do what he's supposed to do, and the fellow in front of him can only see his back and his arms, but he does that too, and so forth and so on, and that's the way the whole boat runs. Well, doing that work, there's a book that I'll recommend to you. It's called The Boys in the Boat, and it's by Daniel James Brown. And it's a wonderful story. It talks about the University of Washington and how it got to Berlin in 1936 and beat out Adolf Hitler, who had conspired to put them in a position where they would have a disadvantage, and they won anyway. And in that book, you see that the grunters have to hold the oar correctly. They have to put it in the water so that it doesn't splash. They have to pull with tremendous force. They have to get it out of the water without grabbing any water. If they do, they've caught a crab, and that may cost the race. And you do that for 300 to 1,000 or more strokes in 10 or 15 minutes, and it is very painful. The lactic acid is pouring out because all of the oxygen is being used, and yet they do it. Now, he did that for all 4 years, is what I learned in college. And all the while, he was learning how to, get interested in science or whatever else he did in college. And he was in my lab, and he was a star. So I think that may have been he has done that kind of work all his life, I think. And the results are obvious. But anyway, I'm sorry I took some extra time.
Thanks for joining us.
But I wanted to get that idea across.
Thank you.
Thank you. So Sydney predicts that you're a persistent, hard-driving, hard-working scientist. I want to take you back, if I may, to the 1970s and let you explain that period of time when you were working on Scrapie and trying to identify the infectious nature of Scrapie. You've been a Howard Hughes Medical Institute investigator, and they didn't think you had wind in the sails at that time.
That's true.
You had a lot of skeptics, and it was very hard work. So why don't you tell the audience a little bit about the strategy that you took to try to unravel the infectious nature of Scrapie?
So maybe back up just a little bit, because it begins with a patient. When I was a resident in 1972, and the patient comes into the Moffitt Hospital, which is in San Francisco at UCSF. And this woman from Marin, a nice-looking woman who's about 60, she can't put the golf balls in her golf bag. She can't put her key into the car ignition or into the door lock. And she's getting worse by the day. And I don't know what's wrong with her, but she has a rapidly progressive dementia. And the attending said, oh, this is Creutzfeldt-Jakob disease, or Jakob-Creutzfeldt disease. And I asked, what was that about? But I really didn't get into this until the attending changed. So the patient was on the service for about 4 weeks. That was when we didn't have all of this managed care and this tremendous pressure from insurance companies. And so the next attending rotated on, who was a neurovirologist. And he started to tell me about all of these studies where only 4 years earlier, the disease had been transmitted to apes and monkeys by Carlton Gajusek and Joe Gibbs at the NIH, and that there were analogous studies with Scrapie of sheep. It had been transmitted into mice. So there was a little bit known about tremendous resistance to breakdown by UV radiation or X-ray. And I got really excited about this because I saw this I learned all this chemistry as an undergraduate here, and I had really liked biochemistry in contrast to most people who didn't really like biochemistry as a course in medical school. So now I'm confronted with a patient, and I start to read, and I see that there's this an enigma. Nobody knows what causes this disease, except that it's transmissible, and therefore you have a way of measuring it. And then I say to myself, well, this is just like across the street here in the chemistry building, there were unknowns, and you could figure out what it was. You just went through a series of measurements, and it wasn't that hard. And if you saw this as a chemistry problem, you could solve it. And I knew that there were lots of people with Alzheimer's disease, but nobody had a way of approaching that at the time. So I saw this as a really interesting problem, and I still had the research bug that I caught with Sydney. And I wanted to do something. And I had been at the NIH for 3 years before that. Instead of going to Vietnam, I was extremely lucky because I learned a huge amount of enzyme chemistry. So that's how I began. And I was there trying to figure out what to do, how to approach this. And I spent the next 2 years as a resident reading everything I could, not about strokes or other diseases that were pretty common, but what was known about scrapie. So I had 2 years in which I could read every single paper, analyze the data, as Sydney had taught me to do, and now I was ready, and that's where I started.
So this was with Earl Statman at NIH? Was
Right, yes.
And I remember when human growth hormone got taken off the market because they had been extracting pools of human pituitary glands because you couldn't use other species for growth hormone. You couldn't take bovine or porcine. And what was discovered was that, some of the patients contracted Creutzfeldt-Jakob disease, and it was an example of transmission in humans.
So that's 1985, and the first case was in southern, the southern Bay Area to the south, and that this was a young man who was about 25, 28, who had been given growth hormone for 5 or 6 years. And it became clear that about 1 in 10,000 people have Creutzfeldt-Jakob disease, and that's the size of the batch of pituitaries that were extracted. So theoretically, every time you could have Creutzfeldt-Jakob disease agents, as they were called in those days. And at that point, we could detect the prions because we had antibodies that we'd made. And so the case was very clear. It was nailed down very rapidly.
So you were faced with the literature that said there's an infectious agent, it's transmissible, you were trained as a chemist and biochemist, but this was the era of recombinant DNA technology and virology.
Right.
All the rage where people could clone plasmids, and why don't you, without getting into detail about the biochemistry, I think it would be helpful for the audience to hear the steps you took to try to define what was the nature of the infectious agent.
Well, it ended up that the time with Earl Statman for 3 years, purifying an enzyme that was very rare, glutaminase, the levels were extremely low, that was a primer for everything that I did, because it turned out I was trying to find a protein. I didn't know what it was, but there I was, had all this experience, and so I thought, okay, the way to do this is to take many brains from mice and then try to systematically go through, as you would do in any unknown, looking for what by some method of measurement that you would then enrich for this activity. And you had to make a spreadsheet, kinds of things that Sydney taught me to do. So you needed to know, and Earl Statman taught me to do, you needed to know how much you started with. You had to do all the math all the time at every step. So if you were losing the activity, then you knew that was a bad step, and you had to try more and more possibilities to continuously enrich. And it didn't go very well with mice because I needed 60 mice in a year to get the data. Now, it turns out that I could get the data in about 250 days. It didn't change in the last 100 days. But that still was useless because that meant that I had to go 100 days. I had to do something in between. And then I could take that information and go again for another 100 days. And pretty soon you run out of time. So the first place you run out of time is tenure. And I would go to meetings and present what I was doing, and people would raise their hand. I would say, "Do you have tenure?" And I would say, "No." And then they say, "Why are you working on this problem?" And I would say, "Well, because it's interesting, it's fascinating." And they said, "Well, you should not be doing this if you don't have tenure." So that was the big hurdle. But then came hamsters. And when I saw that hamsters could get sick in 70 days, in contrast to 120 days or 130 days, and that they had 10 times as much of the scrapie agent, as it was called, I said, this is much better. I can develop an assay with 4 animals, not 60. I can get the data in about 100 days, and instead of 300 plus. And I start with a 10-fold enrichment, which meant that it was like a purification 10-fold in which you didn't lose anything. So here I was starting up at a much higher level. So this broke the whole problem open.
So the tenure clock is ticking.
Yeah, well, that's another problem.
You're trying to get the specific activity up as high as you can. And I mean, one of the tests that I've seen in your papers was to try to add different kinds of treatments that would eliminate the infectious agent. Yeah. Could you irradiate it? Could you freeze it? Could you heat it? Could you digest it away? And it's a little bit of a shotgun approach, and it requires being a crew member to row through all of these things, a lot of persistence.
Well, what you wanted to know is if it really was a protein, then you wanted to know that's very important, because then you wanted to add inhibitors of proteases so that your preparations, which became more and more pure, weren't destroyed by a protease that was in that preparation, or a nuclease, which was going to destroy the nucleic acid. So it was really important to learn as much as I could at every step along the way. And then as time went on, it became so clear that there was no hint of DNA or RNA. And this, all of a sudden, I said, this is a gift from the gods, to have something that behaves like a virus. It looks like a virus. It smells like a virus. These people used to write papers like that. And they'd say, and whatever Stan Prusiner thinks, it's a virus. And he's just wrong. But this was a gift, that there was no nucleic acid, and yet it replicated, it multiplied, and it multiplied 100,000-fold, 1,000,000-fold, 10,000,000-fold. So that's how it evolved over time.
So in your CV, one of the things that I noticed from this period is that you're the first author on many of the papers, and they've all got a writing style that I think is your voice. One thing, and you and I haven't talked about it, but for projects that are this difficult, this challenging, tell us about having people come and join you in the laboratory and collaborate, getting graduate students and postdocs. How did you excite people to come and join this journey with you?
Well, I couldn't do graduate students because I had all these people in the biochemistry department who said, Stan Prusiner's crazy, you'll never get a PhD out of this, and don't bother to go. And of course, these were all biochemistry graduate students. So that was the end of that. And I said, well, okay, I don't really need these people because I don't really want to spend time teaching them what to do. I'll just get postdocs. And so I would get a few postdocs here and there, and then they were really pretty terrible. I mean, one of them came, and and I had met him because he got a PhD from Berkeley, but working in the Naval Bioscience Lab, which is gone now. But that's the place where they used to release anthrax in World War II over the bay, and try to then recover it. So, so this guy, he came. And he was strange from day one when he showed up, and I thought, oh boy, this is going to be a mess. And after about a month and a half, I called up the vice chair of psychiatry, who was a friend of mine, and I said, you got to see this guy. We'll call him X. And he went, so X went to see the vice chair. And then I sit down after a couple of sessions. I'm not there, of course, but now the vice chair gets to know him, and he says, listen, this guy is seriously ill. And he said, you have to continue to employ him, but you don't want him coming to the lab. So I had to sign all these timesheets so he would get paid from an NIH postdoctoral fellowship. And now, 10 months go by, and I said, Leon, the vice chair of psychiatry, I said, Leon, what am I going to do? I need to stop. And he said, no, you're going to continue to pay him. And in the back of my mind, when I first started trying to run an operation, I had read a New York Times Magazine article about Adam Clayton Powell, who was a US congressman in New York. And he's sitting at his desk one day, and in comes a former, he thought, happy, satisfied employee who came in with a gun and shot him and killed him. And I always used to get this image that it's not a good idea to have employees who are disgruntled. They need, and even that doesn't guarantee anything. So I said, okay, Leon, let's go for another year. And then another year went by. They, okay, Leon, we're finished. No, there's one more year on the fellowship. Then we went through the whole thing, and then the guy disappeared. But so it was really hard, and I had terrific technicians, and they were the focus of making everything work.
So one of the challenges with this hypothesis...
That's why I wrote the papers.
Good, well, good for you, it worked out. No, and for those of you who have had a chance to look at some of these seminal papers or review articles, there's a rigor in the analytics that comes through all of them. You know, there are 6 possibilities, and there are 3 tests to rule in or rule out each possibility. It has a certain style about it. But one of the challenges with ruling out nucleic acids, whether DNA or RNA, is that it's hard to prove that there's not a tiny little bit or a small fragment. And I mean, at the end of the day, it's just a hard thing to get rid of. And I suspect that reviewers were relentless in their criticisms about this. And when were you convinced, and why were you ultimately convinced that this was a solely proteinaceous product and not some kind of nucleic acid virus?
Well, so it really travels along this path of finding the protein and then getting Lee Hood, who was at Caltech at the time, to help me sequence the amino acid sequence, because I knew if I could get that, then I could do molecular cloning, which had just been developed. But again, the people who were the biochemists in San Francisco, who were now the molecular cloning people, they really had no interest in this problem. They still thought I was completely crazy. They couldn't get rid of that idea. So I ended up with a guy named Charles Weissman, who was in Zurich. So together we did this. We needed the piece of DNA that was determined by the amino acid sequence from Lee Hood, but that's how we've retrieved it. And then we found that with this probe, we could look and look and look whether there was an RNA or DNA genome. So was it a virus? Because that would be encoding the protein, which was necessary. And what we found very quickly was that in every organism, without any scrapie or anything like Creutzfeldt-Jakob disease, the DNA and RNA were found. So therefore, now there had to be some difference. And immediately we found that we'd already found this a while back, because to purify the scrapie agent, we had added limited amounts of protease, because that's the best purification there can be, is you can chew up everything else. And we had found that it was resistant. So now what we did was we said, gee, maybe there's a difference between the scrapie form and the normal form, which was being produced by the RNA and DNA. And the answer was yes. One is protease resistant, that's the infectious one, and one is protease sensitive, that's the normal one. And then later it became a little more complicated, but we now had more tools, and we could see that there was also a protease sensitive infectious one. But that was minor working this out.
So I want to ask you a question, and then we'll switch gears into some of the various disorders. But I'd like you to walk us through the naming of this agent and how you came up with the name, and tell us a little bit about why it was controversial and maybe the importance that it's had for the field as a whole.
So the root goes back to I.S. Ravden and the precursor of Ravden, which is my aunt in Philadelphia. And she's the one that calls up Ravden, and Ravden creates this opportunity with Sidney. So later, she introduces me to a man named Frank Westheimer, and she and Frank Westheimer's wife were classmates from beginning age 3 in nursery school. And they were friends until my aunt developed Alzheimer's disease at age 80. So Frank Westheimer is coming to visit me in San Francisco because he's there to give a week-long series of lectures in pharmaceutical chemistry. And I had told him a little bit about this, then I went back through it and showed him the data. And he said, Stan, a little bit more and you are going to find something unbelievable. It's extraordinary what you've done. And he said, you need to listen to me now. You need to come up with a good name. He said, if you don't come up with a good name, excuse me, then somebody else is going to come up with a good name. And that person is going to get a disproportionate share of the credit. I said, I can't let this happen. I got to come up with a good name. And then I thought, and I said, I need some Greek professor in Berkeley. And I knew a lot of Latin from high school because I took it for 5 years. But I don't think there's anything going to be there. But I thought about it a little bit. But I couldn't find a professor who was interested in this kind of topic. I never made it to first base. I didn't even know how to find the people who were interested in who were Greek professors. This was going to be a big deal, so I gave up on that. And then I started futzing with letters and words, and I thought there's got to be some little tiny bit of logic behind this. I can't just throw out something. And then I said, what kind of words are good? They're 5 letters. They're two vowels generally, and they're 5 letters, and they got to sound really good. And I started it, and I had protein, and I had infectious, and I had agent, left over from Scrapie agent. And the first, then I would go to the lectures where most lectures are boring. So you sit there and you write out all these possibilities and don't have an iPad or you don't have an iPhone, so you can't look at the stock market like most kids are doing in classes all over the world. So I come up with protein, infectious, so it's PI, agent A, and then I come with an F, so it's PF. And of course, Edith Piaf, you'll think she's great. And so I tried this on one of my friends, a guy named Sidney Udenfriend. And he writes me back a day or 2 later. He says, Stan, this is not okay. This is an American discovery. This is not a French discovery. So get rid of that. So I threw that out. And I liked Edith Piaf. And, and Piaf means sparrow in French, so I now had to come with, so I threw out agent. That's non-specific. So now I had protein and infectious, and then I said, well, okay, so if I write protein, PRO, and then I take IN, now I get proin or proin. And then people have written about this, and they said, well, it rhymes with loin, so it's probably a good idea. So that went nowhere. And I have no idea how many times I stumbled across this transposition of PRION, where I shifted the O and the I. But one day it finally hit me that this looked really good, because ion is a great word. It's 2 vowels, and it's only 3 letters. And it sounds like good. This is some kind of primary particle. So I now leave. I'm eating lunch by myself, looking out at the Golden Gate Bridge from this defunct faculty club. And I walk upstairs, and I pulled out Webster's Unabridged Dictionary. And there is prion. It's a bird. It's a petrel bird that flies from Tasmania to the Antarctica and back every year. And I said, who the hell has ever heard of this bird? And it's pronounced prion. And I've been calling it prion. So I said, okay, I'm going to leave it prion, and no one will know about this bird. And if I'm right, the bird will go down to definition 2, and prion will be definition 1. So that's what happened. Mm-hmm. And then the shit hit the fan. Because, you know, if you give something a really good name, the whole field now becomes subservient to this name. And there are people who don't like that. And there's still people today who are still grousing about this. And it's fascinating to have lived through this. And I had one guy who was a friend of mine from Australia, and he wrote me a note about 3 years after I had introduced the term. And he said, Stan, why don't you just put that away for 5 years and see if it's meaningful at all after that time? Of course, betting that everything would just disappear. And I wrote him back and I said, Colin, I wanted to say shove it up your ass, but I didn't. It was close. It was really close. So that's kind of the story.
Well, I think that advice turns out to be pivotal because it gives an identity to an agent, and there are going to be skeptics.
Yeah.
There are going to be people that get behind it. When you look back, and obviously you have, I think that was a critical moment. A lot of people here aren't in neurology, maybe haven't followed this. We talked about Scrapie, we talked about Jakob Creutzfeldt, but give us a short list of some of the other diseases where this kind of agent is relevant. And I know it's a long list, but I think it will impress people that don't track it to know how important this is.
So let me just give you the history of this, because here it's 1982, I introduced the term prion. The same year, later that year, we find the protein, so we call it prion protein, PRP. It's just for Scrapie. And then 1983 comes, and I have been looking and looking at these electron micrographs over again. And I have a collaborator, an advisor, Robley Williams, who was the first person to see a virus in the electron microscope in the United States. And so the microscope was invented in Germany in 1938. So we would look at these things, and we didn't really understand what we were seeing or why we were seeing it, what this was like. But it looked like kind of a rods, that's what he would call them. And I would just look at this stuff, and then one day I look and I'm paging through a book on electron microscopy of proteins. And there is a chapter on amyloids, and whether it's isolated from the spleen or the liver or anywhere, these purified preparations, they look exactly like what I'm seeing. And they have violated the first law of viruses. The first law of viruses is that every single virus that's polio looks the same by electron microscopy. And every tobacco mosaic virus looks the same. And so he kept saying to me, Stan, this stuff doesn't look like a virus. And I said, well, it's amyloid. And he says, well, how are we going to prove this? And I said, we got to get somebody who knows how to do stains with Congo red dye. That's the tinctorial property, because now there's a birefringent property. So when you stain it with the dye and you now look by polarized light, it goes from gold to green to gold every 90 degrees. It's pretty simple. And I can't find anybody in the Bay Area that knows anything about amyloid enough to tell me what to do. So there's a guy from the NIH named George Glenner. He's on sabbatical in San Diego. I call him. He says, yeah, come. And I take one of the postdocs. There's no TSA, so we just walk right onto the plane. We have a little box of ice. We have the most purified preparations that we could produce. And we get on the plane and we fly to San Diego. We get off, we rent a car, we drive to UC San Diego where he's on sabbatical, and he takes a drop. He puts it on the slide, and now it's dries. And he looks by bright field, and there it's red. And then he turns the polarizers on, and he looks, and he is blown away. It's gold, green, gold, green. And he said, this is amyloid. Well, he had been trying to purify the amyloid out of Alzheimer's brains. And he finally succeeded in doing that a year later. And of course, it had the same properties. But it was already known that it was amyloid. So now you just step back from this and you say, okay, we have this purified protein. It is the cause of the disease, and it stimulates more of itself to be made. Well, how many other amyloids are there? Because people had been doing this for 100 years. And then you say, whoa, this is Alzheimer's disease. This is Parkinson's disease. And the list goes on. And you say, this is unbelievable. We've just discovered the diseases are all prion diseases, or many of them are. And boy, if you've been working on Alzheimer's disease for 10 years and somebody writes a paper in Cell, so it was a very prestigious journal, and it lays out all of the logic, and you see this, you've got to be really upset. So that was the next thing that happened. So now I went from Scrapie to everything in the degenerative disease world. And that was not fun to have. I mean, that's just what every scientist hates, right? Scientists are, the one thing that worries them is that they will miss the discovery. They've been working on this for 10 years or 20 years or 30 years, and there's no chance. I mean, okay, the 76ers have a chance a year from now to win. And the Eagles, well, maybe they can win it again. But if you've been working for 10 years on something, there's no chance. It's over. The game is over. And so people were really resistant to this. They didn't want to believe this, that this could possibly be the case. That's a long-winded description.
No, it's a fascinating story of serendipity and discovery and finding the right people to help you out to solve a problem. So as this story is starting to unfold, you begin with a pretty uncommon problem in an animal model, and now it sounds like a lot of the neurodegenerative diseases, certain forms of Parkinson's disease and Alzheimer's disease and what we used to call Shy-Drager syndrome, multi-system atrophy. So the list goes on, and I guess what we're all thinking about now is you've got the pathophysiology. What does this mean therapeutically? How do you and others in the world think about how to use this information to either make the diagnosis or develop new treatments?
So after the Nobel Prize, I thought, okay, what am I going to do? Am I going to become a dean? I already had an offer. Came quickly. And I said, no. I said, you know what? I want to develop a drug for at least one of these, because one drug could open up the whole field. And I started by doing this with Scrapie, because I had the best animal models. I knew more about that than anything else, and therefore I ought to be able to do this. And I managed over 10 years to assemble a small group of people, but the problem was that the medicinal chemistry side of this was foreign to me. And it was just a repeat of everything that happened when I first started with Scrapie. I couldn't get any highly trained, fabulous people to do this because I didn't have a track record. And it wasn't clear that, you know, the medicinal chemists, they already wanted one example. It was just the same thing. And I went through 10 different medicinal chemists, because you need to start with one before you get 2 or 3. And I had to get rid of one after another because they really didn't know what they were doing. There was a reason that they wanted a new job. I found out. So anyway, after 10 years, we made 10 drugs. And so the incubation time was 100 days. We doubled the incubation time, or we tripled the incubation time. And in one case, we quadrupled it. So the mouse was living almost as long as it would live without scraping. So that was very successful. But then I said, okay, you know, it's time to stop. We got to move on. And then it was just like deja vu all over again. I needed a lot of money. Now the NIH was impossible. I had 3 program project grants, and that wasn't even scratching the surface of what I needed to build. I needed to build a unit with 20 medicinal chemists at least. I had to have many more animal models, and I had to move from 10,000 mice to 20,000 mice. And on goes this list, and this incredible equipment, like you heard, many of you heard from the chair of biochemistry about cryo-EM. And I said, I gotta have a cryo-EM group, because if I don't have that, there'll be so many other projects that people will want to use cryo-EM for. I won't have a chance. So I did this. So now it's come together, and I had to get drug company support, and I had to find other philanthropic support to make this happen. So, you know, if you think you're on the verge of something, it means nothing, because if you don't have something. But we then made a wonderful discovery, and it really begins at Penn. It's Milton Shy, who was here when I was a medical student, and he was the chair of neurology. And this was in the late 1960s, before he went to Columbia, and he died there very prematurely. I don't know what they did at Columbia. That's supposed to be funny, I'm sorry. Anyway, when he was at the NIH in 1960, he described a disease in which people would stand up and they would get orthostatic hypotension and they would fall over. So internists focused on this disease, not neurologists. And then through the 1960s, there was a shift, because clearly there was a lot of neurodegeneration in the spinal cord. So this disease eventually went from Shy-Drager to multiple system atrophy. And I knew about this, but I really wasn't interested, because the neurology was so esoteric. It went on, trivia, I thought. So then, in building these models for Parkinson's and for, excuse me, for Alzheimer's disease, we now had one for Parkinson's, and I had spent a year writing that book that we mentioned, Madness and Memory. So there's now a neurologist at Imperial College in London, and he's also the president of the Parkinson's Brain Bank in London. And I'm having lunch with him, and we still haven't figured out whether the lunch was in San Francisco or was in London. I say it was San Francisco. So he could be right, it's not. So anyway, I said, Lefkos, send me some samples of Parkinson's brains, and let's see if this new approach that we're trying to take will work. So he sends me 2 Parkinson's samples, and he sends me 2 of multiple system atrophy. And I must say that I didn't really know what the hell he was doing, because I hadn't thought about multiple system atrophy. And it was 1998 when people first showed that synuclein was in these big, almost amyloid plaque-like regions in the oligodendrocytes that make the myelin. And so there's synuclein there, and there's synuclein in Lewy bodies. Well, we inoculate all the samples, because that was the easiest thing for me to say to one of the postdocs, inoculate them all. I don't have to sit here and tell you why. And 100 days later, the samples of MSA kill the animals. And in fact, the animals were animals we got from Virginia Lee and John Trojanowski. These were transgenic mice that made a lot of synuclein. And we had other animals from San Francisco, from Bob Nussbaum, who's the one who figured out that using genetics, that synuclein was the key molecule in Parkinson's, and that's what led to the immunostaining eventually. And those mice don't work very well. So now we knew that we could take brain from people with a different prion disease, a synuclein prion disease, and if we inoculated the animals 100 days later, they would die. So we had 2 samples, and then we didn't know. Is it 2 out of 2, or is it 2 out of 2 million? So then I went and I tried to get other people to do this, but I couldn't get them to do it. I don't know why. But we got 20 more samples from 3 different continents, and it was 20 out of 20. And then we knew there was no issue. This was not a 1-off or a 2-off odd result, or it was a contaminant. So this has just opened up the whole area. And now we actually have a lead compound near a drug, which is extending the lives of the animals. Now, it's not big enough, but when we get it a little further, then it's gonna rapidly go to phase 1, and we'll see where this goes.
Well, that sounds encouraging. So I want to circle back to where I started, and I didn't really fully introduce Stan Prusiner, but you will have figured out now, if you didn't know already, that he has been awarded a number of prizes and elected into the National Academy of Medicine and the National Academy of Sciences, and he's received the Gardner Prize from Canada and the Lasker Prize and the Nobel Prize. What I want to observe is that not all of these discoveries are really on the same playing field of impact. I mean, this is one that required a certain amount of genius and persistence. Maybe it did come from the crewing, rigor of research, and staying the course through a lot of challenges. And now we've got much better understanding of pathophysiology and the possibility of treatment. So when I turn this back to you, and you've received the National Medal of Science from the President of the United States.
That was Obama.
Yes. I mean, it must feel to you like some mixture of appropriate recognition, but also a weight of an obligation that you're sharing with us now about, now I feel the heat to find some treatment. Maybe you can just describe how it feels to go through that kind of discovery and recognition process.
Wow. We've almost run out of time, so I don't really have to do this. So, when people are, when there's a Nobel Prize being talked about, you hear about it, then each fall you don't get it. And then you begin to think, and this is unsaid by other people, well, you were supposed to get it. What's wrong with you? Something's wrong with you that you haven't gotten it. And so you kind of live through that. And for me, the thing that I wanted the most was a parking place. Because I had to walk so damn far from my car, find a place to park my car at UCSF. And it was getting ridiculous because I only lived about a mile and a half away. And pretty soon it was already a half a mile. So I thought, God, this would be really wonderful. And then I got the Lasker Award. And so the dean, who was a neurologist, Joe Martin, he said, okay, we're changing the rules. If you get a Lasker Award, you got a parking place. And then I said, that's great. I don't really care otherwise. So the next year, there was nothing. And then the next year, I'm really not too interested in this process because I can't control it. And if it happens, it happens. And, you know, one of the things that happened to me here at Penn was after Sydney, I worked with Britton Chance. And Britton Chance was somebody who was so smart and did so much great work, but he spent his whole life once a year going completely crazy, not getting a Nobel Prize. And he was so upset, and I knew him very, very well. And I watched and I swore that I would never let myself behave this way, and it helped me a lot in life. So then this just happened, and it was great. It was fun, and it was nice, and it opens up lots of doors. But you can do one of two things with it. You can either stay focused, and you can really use it to do something important, because this was, from my point of view, prions were just the beginning. It was drugs. As physicians, we want drugs or some other therapy. And so I said, okay, I know what I want to do. I want to create a drug. And we managed to create 10 drugs, but they're not for humans. And there's a barrier because we can't do it in Creutzfeldt-Jakob disease because nobody's ever created a cultured cell in which the human PRP prion multiplies. So you have to have this high throughput screening method. You make lots of, they'll be similar to Scrapie, but you need a method to do this, and we don't have one at the moment. So we moved to these other pathogens, and so we really are studying now tau prions and synuclein prions. That's our focus. And for me, it's great. You know, one of my very close friends named David Ramsey, and we work together every day. We look at each other and we say, you know, we don't need another paper in our lives. We need a drug. That's all that matters. We don't need to write another paper. So it takes away all this stuff about we gotta be first, but it's still going on because there are these young people and we gotta help them and make sure their careers are being fostered, and we need smart people. So you have to deal with that. But the real focus is this, because I think this is the most important thing I can do. And it's great. It's really great to be able to do this, and I wouldn't be able to get the funding if I hadn't had so much recognition in the past. That's the key to being able to make this happen.
Well, it's a privilege for us to have an hour to hear your story, and I'm so happy that Joe Martin had the wisdom to give you a parking place when it was all said and done. That's why he became the chancellor, such a smart guy, that when you win the Lasker, it's time for a parking place. But it's a fascinating story. This is going to have huge societal impact, and I think it's a lesson beyond the prion story itself. And you've shared some of the allegory of those lessons along the way. And I think all of us would like to give you a round of applause.
Well, thank you. Thank you.